pH. So that might be part of it. And if your plants are in the cycle where they're dying, they're going to be using up oxygen, so you're going to produce more carboxylic acid, so your pH will go down. So a lot of it will depend on what cycle you're actually in, if it's growth or decay.
Thank you very much, Dan. You're teaching all of us biologists. And so it's your turn to go and tell us about your biofuel project.
All right, thanks. When I started this project, I started it with two main goals. The first one being, if I was a teacher looking to start a biofuels lesson, if I found this website, that I'd be able to basically make that lesson a lot easier. I was trying to compile just general information, some labs and stuff, so you're not basically starting from the ground up, which I found lessons similar to this that I could build off that just make life a lot easier. And my second goal was to have students actually create a biofuel in the lab environment, whether it was my lab or somebody else's. I think the students actually having the ability to create this stuff really makes for a lasting impression on what the process actually is. So this is kind of a general overview of what biofuels are. So the first one, let's see. All right, yep, not in order. Let's see, right there. Yes. All right, first one, what are biofuels? Biofuels are short for basically what's called a biologically based fuel, generally meaning it comes from some sort of plants. Basically, we take plants and chemically change them into fuels that we can burn in transportation, electricity, and other things that we use energy for. So what plant we use and what process is all depending on what we're trying to make. So first, trying to find the slides here, bear with me. All right, so the first type we're going to look at are alcohol-based fuels. You guys have all probably heard of this one. It's the most common biofuel that's currently used is ethanol. Ethanol is mixed in pretty much all the gas that is in the U.S. today, the basic 87 octane. So if you look on the bottom, it's the general structure of ethanol with the carbons, the hydrogens, and the OH. Pretty simple molecule. It's made of one of two processes: fermentation, which has been around forever, and cellulosic ethanol, which is kind of a new, really promising method that we'll get into a little bit further along. All right. So these are just some pros and cons of ethanol. Pros being, obviously, if we're burning ethanol, we're not burning petroleum-based products. Reduces emissions, which, as we've talked about global warming and stuff a couple times here tonight, is obviously a big deal. And if produced correctly, it has the ability to be produced fairly efficiently, meaning that we get more energy out of it than we put into making it. And a couple cons, there's the food versus fuel debate. Basically, are we making fuel out of stuff we should be using to feed people? It doesn't mix with gasoline all that well, and the big problem is that it can attract water, which doesn't really burn well. Next slide. All right, right here. The second, alcohol-based fuels, and the one that I believe we should be using if it wasn't for billions of dollars behind the ethanol lobby industry. Biobutanol. If you look at the chemical structure down there in the right corner, you see that it's similar to ethanol, but there's more carbons. Basically, the more carbons there are, the more energy is contained in one little molecule. So biobutanol is much more energy dense than ethanol, which is one of the issues with ethanol. It's about 40% less energy dense than gasoline. So basically you need more ethanol to go the same amount of distance that you would with gas. Biobutanol fixes this problem. It's about 95% as dense as gasoline. Biobutanol also can be produced from stuff that isn't food. Switchgrass, cellulose, wood, basically waste. So biobutanol's got a lot of potential, and it's starting to actually be produced on the industrial scale. Now, if this was the first time I talked about biobutanol, I think it was really starting to come on. The first time I talked about biobutanol was probably about 12 to 14 years ago at a regional envirothon, and it hasn't really grown much. So I think there's hope for it, but it's not happening quickly. And it's kind of frustrating to see something that's this promising and then isn't really happening. And what I mentioned earlier, cellulosic ethanol. Yes. Basically, this is just a different way to produce ethanol. Right now, there's two countries that produce a lot of ethanol. The U.S., meaning us, and Brazil. The U.S. uses corn to produce ethanol, which is the worst possible thing to produce ethanol from, just from an energy and an environmental perspective. So from an environmental perspective, corn takes up a lot of room, produces a lot of fertilizer runoff that creates that nice, huge dead zone in the Gulf of Mexico. And then when we use it, we produce a lot of waste in the fact that the grain is all we use to produce the ethanol, and all the other stuff is left behind. Cellulosic ethanol solves that. Cellulosic ethanol basically breaks down the actual cellulose that makes up the plant stalks and everything on that plant, and then creates ethanol from that. So we're no longer wasting the corn stalks. We're no longer wasting the leaves out of your yard, or if you had a tree cut down. That can all be now turned into ethanol. If you look in the bottom left-hand corner, those big bales that look like hay bales, they're actually corn stalks that were harvested, and now we're going to be turned into ethanol. So cellulosic ethanol is a really big possibility for the ethanol industry if we could get away from just using the corn grains. And the next one is oil-based fuels. So the first two are alcohol-based that we can mix with gasoline-type engines. Oil-based fuels are biodiesel. Basically, they can replace the normal petroleum diesel. Biodiesel is great in the fact that it has a huge net energy gain. So to break even, say you need to get out as much energy as you put in to make something. Ethanol is about like 1.4. The break even is around 1. So it's slightly positive. Biodiesel is around 8 to 10, depending on what you use to produce it. So biodiesel, you get a ton more energy out than what you put into it. So biodiesel is an oil-based fuel, and you can see in the bottom right-hand corner kind of the cycle. We start off with an oil crop, whether it's like sunflowers, rapeseed, soybeans, and then we take the seeds, process it, and then burn it in the vehicles, which then produces CO2. But it's CO2 that the plant's already absorbed, and we're going to produce when they decayed anyway. So the thing about these fuels is they're fairly carbon neutral, meaning they don't produce any new carbon. And then the cycle starts all over again when the plants regrow and reabsorb the CO2. So using these plants to produce fuels, making them carbon neutral, we're not adding to the global warming problem. We're not increasing CO2 at all. Another thing is this slide. Here's some pros and cons, but what I want to look at right now is on the bottom right-hand corner. You see that bar graph, and about, I don't know if you guys can read it, but the line right from the top is the zero line, and that's measuring emissions. Every single emission, when you compare biodiesel to regular diesel, declines hugely, some along the lines of 60 to 80%, except one little blip, nitrogen oxide, that goes up 10%. So not only is it better for the CO2, but it's better for the environment because we're not adding any more other pollutants to the environment. A lot of these pollutants are what causes acid rain, which we've minimized over the years, but it's still a big problem overall. So I'm going to move on. I see somebody in the text box said something about algae. So here you go. Algae. Algae has a huge potential. It was estimated that if we covered 15% of the Sonoran Desert with an algae production facility, that we could produce enough fuel for the entire country every single year. Everybody's seen algae, and the pond biodiversity study we just got done with. Your pond's probably covered with algae from time to time. Well, there's certain types of algae that are very high in oil content. The nice thing about algae is you can grow it about anywhere that you can take water and feed it with carbon dioxide and little nutrients. This also ties nicely into the wastewater treatment study we just did. What they're doing with these algae plants is that they're running the wastewater through the algae production area for nutrients. And they're also taking CO2 made from coal-powered power plants, and they're running it through to provide the CO2. So not only are we producing fuel, we're treating wastewater, and the fact we're using it as a food source, and then it comes out the other side of the algae clean. We're also reducing the CO2 produced by burning coal. So algae has got a lot of promise, and the fact that, let's see if we can, yep, let's go back one more. If we go back, that graph on the bottom left, that's how much biodiesel is produced per year, per acre, using different crops. So soybeans and sunflowers are the main crops right now, and they're all the way to the left. If you go all the way to the right, that huge peak is microalgae. So microalgae has huge potential. Now we're gonna have to skip ahead a little bit and go to the website. All right, right here. Here is what I want teachers to be able to find when they want to develop something that has to do with biofuels. I want them to be able to find this website and find the general information. So on the left is each biofuel. And if you go down to the bottom left there's the teacher materials. Basically, the labs, in order to develop this stuff in a laboratory environment, are there. This presentation, and a bunch of videos that would get a classroom interested in what biofuels are and why they're important, and basically what energy is. And then if you click on the left there, ethanol, biodiesel, biobutanol, there's a short description and a informative video, a lot of them from the Department of Energy, that tells you basically how they're made and why they're important. So without running up time too much, sorry, those are the labs that I have in that website, along with this PowerPoint. So reputable sources: University of Chicago, Clarkson, and U.S. Department of Energy. So without any more time, anybody have any questions?
Did you see did you see Michelle's question?
Yep.
Yeah.
As far as what's holding them back at the moment, cheap oil, capital investment, and what's keeping corn the #1 ethanol producer in the U.S.? Subsidies and ethanol lobby. The corn belt in the middle of the U.S. has a ton of money into making sure that they're growing corn, and that's what they're going to keep doing. So unfortunately, they're not willing to change to make other things, because it's always been corn, it always will be corn, is where they stand. So hopefully that changes.
Well, thank you so much. Oh, another question here.
Sorry. E100 won't run in conventional engines without causing issues. Neither will E85. E85 can only be run in certain engines. And one of the issues with higher mixes of ethanol versus gas is they don't play well together. They don't mix well. So E85 has a short shelf life. E100, you need specially modified vehicles. And Dr. O'Connor, to answer your question earlier, adding ethanol does damage our gas mileage, yes.
Okay, I wondered about that. I heard it damages lawnmowers if people get that fuel.
Yeah, it damages lawnmowers if it stays in there too long and it doesn't get used, it gets stale.
Oh, that makes sense. Well, I think this will be a great project, and I'm certainly we have a lot of biology teachers here too. Would be an interesting uh, cross content, so to speak, project as well. And again,
Yeah, very much so.
yeah, this is great, and it sounds like you have a lot of resources for other teachers to use, which is a big goal of this. I'll be asking Brian to come forward, but thank you, Dan. This is very enlightening. We all drive,
Good.
and
Yes.
yeah, so this is wonderful, and we'll have to keep in touch through our websites so that we can share these. So thank you very much. We're going to conclude with Brian, who's coming in from a different class. He may not have quite as long a presentation, and we're running out of time anyway, but he's going to be sharing some of his work. And I'll put the timer on too for you, Brian. But let's see if we can keep it to 10 minutes since you're just by yourself. And I think everybody's been doing a great job being here, but I know they all have to get on with their lives. So thank you. And Brian, if you could take the mic.